In this video, we will show two special trig limits. So the first limit is the limit as theta approaches 0 of sine of theta over theta equals 1. And I want to show that this is true. So we're going to give a proof of this. So before I get into the proof, if I were to just plug in theta equals 0 into this, I get sine of 0 on top, 0 on the bottom, and sine of 0 is 0. So I have 0 on the top and 0 on the bottom. And that's an indeterminate form, so I need some way to simplify this. Okay, so we are going to give a geometric proof for why this is true. So first, I'm going to assume that theta is between 0 and pi over 2. Because theta is approaching 0, it's reasonable to say that it's going to be really, really close to 0, but it could technically be positive or negative. So first, I'm just going to consider the case that theta is positive. It's something between 0 and pi over 2. So one really important thing that I need for this argument is we will be assuming that the theta, the angle we're working with, is in radians. This outcome, this limit actually won't be equal to 1 if theta is not in radians. Okay, so what I'm going to do is now I'm going to draw a picture. So I'm going to draw some axes, and I'm going to make a unit circle. Okay, I'm going to make a unit circle, and I'm going to label the origin as O, and I'm going to make a line like this, and I'm going to call this angle theta. And now I'm going to do a few things. So at this point right here, I'm going to drop a perpendicular straight down to the x-axis. I'm also going to extend from this point right here, I'm going to draw a vertical line and then extend that line from the origin to this point until it connects to make this other triangle. Okay, and I'll shade in that dot, and I'll call this point A, I'll call this point B, I'll call this point C, and then this point over here, I'll call that D. Alrighty. So what I'm going to do now is, first I'm going to figure out, okay, what is sine of theta in terms of the lengths that I have in this picture? So sine of theta, if I work with triangle OCB with that right triangle, sine of theta would be equal to BC. Oh, whoops, I forgot to label this as a unit circle, so my radius is 1. Sine of theta would be BC over that radius, over OB. So that's going to be BC over 1, which is just BC. So that vertical length, BC, should be sine of theta. Okay. The length from O to A is also just the radius of the circle. That's also going to be 1. So what I'm going to do next is I'm going to figure out the distance from A to D. And I can do that if I take the tangent of theta, and this is going to be in the bigger triangle, in triangle OAD, tangent of theta in that triangle would be opposite, which is AD, over adjacent, which is OA. So we have AD over OA, but OA is 1 because it's the radius of the circle, and AD over 1 is just AD. So that tells me that AD, this length, is tangent of theta. So a couple of these lengths of the sides of these triangles we can express as trig functions. So what I'm going to do is I'm going to compute the areas of some of the shapes in this picture. So some of the triangles, and then a sector of this circle, and I'll relate those areas to each other using inequalities. And it'll turn out that one of those areas will really closely resemble sine of theta over theta. Okay, so before I can do that, I need to state a key fact about the area of a sector. This is going to be some geometry review. So the key fact is, if I have a circle, and here's the center of the circle, and I make this sector where this angle here is theta, and I call the radius of the circle r, so that's r, and this is r. The area of a sector is going to be the area of the whole circle pi r squared multiplied by how much of the whole circle this is. So to figure out how much of the whole circle this is, well, this angle is theta. The whole circle is 2 pi radians. So I would need to multiply this by theta over 2 pi. And that is the formula for the area of a sector. And I could simplify this. I could cancel out the pi's and I would get theta over 2 r squared. And that's the area of a sector. I'm going to put this in a little box. So we are going to need this. Okay, so now we're ready for the key idea involving areas. So in this picture, I'm going to add one line connecting A to B. And when we do that, the area of that triangle OAB, this is less than the area of the sector OAB. So the sector OAB is going to be from O to A all the way, including this arc of the circle. So it's a little bit bigger than just that triangle. And that is going to be less than the area of the big triangle OAD. So let's try to find the areas of all of these things. I'm going to zoom it out so I can still look at the picture. So for the area of triangle OAD, I need 1/2 base times height. 1/2, and the base is going to be from O to A, which is 1. The height is going to be the perpendicular height from B straight down to C, which is sine of theta. That's nice. Is less than the area of the sector. So if I use my formula for the area of a sector, it's going to be theta over 2 times r squared, but my r is just 1. Okay, and that's less than the area of the big triangle, which is going to be 1/2 times its base, OAD, its base is still 1, but its height is tangent of theta. Alrighty, so we have this. Okay, so let me zoom it in a little bit now. Simplifying a little bit, we have sine of, let's keep it in these colors, we have sine of theta over 2 is less than, this will be theta over 2, and that's going to be less than, let's rewrite tangent in terms of sine and cosine, and that'll give me 1/2 times sine theta over cosine theta. So seeing that we have this chain of inequalities reminds us, hopefully this looks a little familiar, this reminds us, when do we have chain of inequalities? Of squeeze theorem. And remember, one of the things that we tried to do with squeeze theorem problems was we tried to make the middle, in this case it's theta over 2, look like the thing that appears in our limit. In our limit, we see sine of theta over theta. So the way I'm going to get sine of theta over theta, or something a little bit closer to that, is let's first divide everything, each part of this, by 1/2 sine theta, which is one thing I got to be careful about when I divide an inequality by something is, was that thing positive or is it negative? Because if it's negative, I'm going to flip the inequalities. But remember, we started off by assuming theta is a positive angle between 0 and pi over 2. So in that quadrant, when I'm between 0 and pi over 2, sine is positive. So this is going to be positive. So I don't need to worry about dividing by negative, flipping the inequality. All right, so I've just copied down my inequality, my chain of inequalities, and I'm going to divide everything by sine of theta over 2. Dividing everything by sine of theta over 2, sine of theta over 2, it won't flip the inequalities because sine of theta over 2 is going to be positive. So on the left, this simplifies to just 1, and that's going to be less than. In the middle, this will simplify to, when I divide by sine of theta over 2, that's the same thing as multiplying by the reciprocal. So I'll get theta over 2 times 2 over sine theta. And that gives me theta over sine theta. Okay, and then for the final one, if I simplify this, the thetas will cancel, the sine thetas will cancel, and the 2's will cancel, and we will end up with 1 over cosine theta. So now the middle is almost what I want to have. It's just the reciprocal of it. So let's take reciprocals of everything. So taking reciprocals, we get. So at this point, the smallest term here is 1. The other terms are bigger than the 1, which means everything is positive. So if all my terms are positive in an inequality, and we reciprocal everything, it'll flip the inequalities. So the reciprocal of 1 is 1 over 1, and that's going to be greater than the reciprocal of the middle is sine of theta over theta. And that'll flip this inequality, and the reciprocal of that is going to be cosine of theta. All right, so now we've made the middle part. Now we've made the middle part of our chain of inequalities look like the thing that shows up in our limit. Maybe let me write this theta on the bottom a little bit better. So in a squeeze theorem problem, once we make the middle look like what we need it to be, then we take the limits of the end parts. So let's take the limit as theta approaches 0 of the 1 over 1, which simplifies to 1. So with this limit, there's nothing to plug into. When I plug in 0 for theta, I just get 1. Okay, now let's take the limit as theta approaches 0 of the other end, the cosine theta. And if I plug 0 into that, I get cosine of 0, which is 1. And that's exactly what we want with squeeze theorem. So we say, since these both equal 1 by the squeeze theorem. Our limit, the limit as theta goes to 0, of sine of theta over theta equals 1. All right, so now I want to ask a question, which is, well, what if the theta was negative? What if theta is negative? Because we only considered the case where theta was positive. Okay, it turns out it's still true, and we can show it pretty quickly. So I want to note that sine is, this is in pre-calc review, it's an odd function. And with an odd function, when you take sine of negative theta, an odd function has the property that when you plug in a negative, theta or negative x into it, the negative can pop out, and then you get sine of theta. So that's a property of sine. And cosine is an even function. And that means if I take cosine of negative theta, it'll be the same thing as cosine of theta. Okay, so what I'm going to do is, in our inequalities, let's replace the theta with negative theta everywhere in our inequalities. Okay, so if I look at our inequalities, on the left-hand side, there's no theta, so I'll just keep it as 1. And that'll be greater than, and for the middle term, I'll get sine of negative theta over negative theta. So we'll get sine of negative theta over negative theta. And then that'll be greater than, and I'll get cosine of negative theta. All right, so because cosine is even, cosine of negative theta, that's just equal to cosine of theta. And in the middle, because sine is odd, this will be negative sine theta over negative theta. And now the two negatives cancel, and this will be sine of theta over theta. So thus, we just ended up with the exact same thing, like all the negatives essentially went away. We get the same inequality even when my angle is negative. So the result still holds for negative angles. And that completes the proof. So I'm going to write my symbol for done with proof. I'll write the square and I'll shade it in. But we've just proved this special limit. The limit as theta goes to 0 of sine of theta over theta equals 1. So this was a pretty sophisticated argument. Like, I would say using geometry in this way was not necessarily an obvious first step, and there was a lot to it. You know, we had to use areas, there was squeeze theorem. So I wouldn't expect you to be able to come up with an argument like this on your own. I would say that would be really challenging, but I do expect you to be able to follow what we did in the proof. That's what I care the most about. Okay, so I do expect you to be able to follow things like how we got the areas, how we got those lengths, how we use the squeeze theorem. Okay, so we are on to our second trig limit. Okay, so all of that was just for the first trig limit. We got one more of these to do. But luckily, the second one's going to be a lot quicker because it involves the first one. Okay, so I'm going to highlight this one as well. Super important, so I want to highlight it. Okay, if I were to just try this by plugging in 0 for theta, I would get cosine of 0 is 1, so I get 1 minus 1 over 0, which is 0 over 0, and that's indeterminate, so I would need to simplify. So I need some way to simplify this. Okay, so I'm going to write what we had, the limit as theta goes to 0 of cosine of theta minus 1 over theta. Okay, and I know that limit involving sine. I know the limit as theta goes to 0 of sine of theta over theta. There's just no sine in this limit right now. So what I'm going to do is do something to this fraction to introduce a sine. To be able to do that, I need to somehow relate cosines with sines. And the key identity from trigonometry is that cosine squared theta plus sine squared theta equals 1. So I'm going to somehow, if I could somehow get a cosine squared in here and maybe a 1, maybe I will somehow be able to rewrite that as a sine squared. And the way I will do that is by sort of multiplying by the conjugate. I'll multiply the top and the bottom by cosine of theta plus 1. This is something that may look weird the first time you see it, but it's a technique that is, you know, occasionally useful when we see limits involving things like cosine of theta minus 1, or maybe even sine of theta minus 1, or plus 1. All right, so when we do this multiplication, we'll get the limit as theta goes to 0. On the top, I'll get the first term squared, so cosine squared theta, and then minus the second term squared. 1 squared is just 1. And then over on the bottom, I'll get theta times cosine of theta plus 1. So this equals the limit as theta goes to 0. Well, cosine squared minus 1, if I just rearrange the terms in this, that is negative sine squared. So the numerator is negative sine squared, and then I have the theta on the bottom, times cosine of theta plus 1. Okay, so now I see I got 2 signs on the top actually. So what I'm going to do is I'm going to split up this limit into the limit as theta goes to 0, and I'll bring one of the signs to be on top of that theta on the denominator. And then I'll multiply that by the limit as theta goes to 0 of everything else, which is negative sine theta, and then there's still a cosine theta plus 1 on the denominator. Okay, because this first limit is our first special limit we did. We know this equals 1. Okay, so we're in business now. We have 1 times that second limit, and with that one, let's just try plugging in. If we do that, we get negative sine of 0 on the top, which is 0. And on the bottom, I'll get cosine of 0 plus 1. That's 1 plus 1. So this is 1 times 0, which is 0. And we've shown it. So this one was a lot shorter. It involved the limit we already had of sine of theta over theta. But we introduced this new sort of technique. There's this analog of conjugates that works well for cosine and sine functions. And I use that in tandem with the inequality cosine squared plus sine squared equals 1. So in terms of our goals for this section, we finished goal 1. We've proved these 2 special limits, one involving sine of theta over theta, one involving cosine of theta minus 1 over theta. As we'll see in the next video, these are going to be directly useful for us when we compute the derivatives of trig functions. Also, I forgot to mention this earlier, but when I mentioned this important thing that theta is in radians, I don't want to completely give that away. For like the reason behind why that's the case, it's actually going to be one of our optional homework problems to explore, well, why is it different if you use degrees versus radians? But I will give a hint and say something here in where the video is showing right now changes if theta is in degrees compared to if it's in radians. And I'll just leave that as an exercise for you to think about.